replace the force system acting on the post by a resultant force and couple moment at point O. So we've got this post here. There's these three external forces acting on it. Those aren't the only actual forces acting on the post. You have a reaction force here from this bracket, but we're not doing a free body diagram where we're separating the post from the bracket. We're just looking at this entire setup here as a body with these three external forces. And what we want to do is we want to create an equivalent system, statically equivalent or equivalent from a rigid body mechanics analysis standpoint, where we remove all of these forces and replace them by a resultant force and moment at point O. When we went through the textbook, we talked about how to do this. So the resultant force, which is going to be a vector, right? The resultant force vector is just you sum all of the force vectors that you're trying to simplify. So we would sum these three force vectors. The resultant moment vector about that point, you sum all of the moments of the forces about that point. So you sum the moment of this force about that point, the moment of this force about that point. Those are all vectors. You sum all those moments, but then you also add to that any couple moments as well, right? Couple moments are free vectors, so you just slide those free vectors over to point O. And that's your resultant, like this is the resultant. That's your resultant force and couple moment at point O. Okay. So this is a planar 2D problem. So we don't need to, we can, but we don't need to represent all of these forces as vectors and get position vectors R and do R cross F and all that. We can use the simplified 2D method. So, okay, summing the forces, what we'll do is, again, instead of representing these as vectors, we can just sum the forces in the X, sum the forces in the Y, and then get the vector that way. So sum of the forces in the X. So we're saying that this is positive X, this is positive Y. We've got 200 plus 300 cosine 30 minus, and we'll use this slope triangle, 4 over 5 times 150. And so what this is going to be the resultant force in the X. So F resultant X. Okay, so plus or no, minus. Okay. 339.8 pounds. Okay, now the Y component of the resultant force, we're just going to sum up the Y components here. So 3 over 5 times 150, and then plus 300 sine of 30. Okay, 240 pounds. So the magnitude of the resultant force is 416 pounds, and it's acting at an angle of, so 35.2 degrees. Right, we just did, it's, the resultant force is, you know, at point O, it's like this amount in the X and then a little bit more in the Y. Well, you do, it's like this, a little bit more in the Y. So the resultant force is, you know, like that, and then there's that angle theta. This is FR. Okay, now we moved all of these forces. We just summed up the forces and replaced them with the resultant force vector. But it's not an equivalent force system because we have to account for the moments that these forces are exerting about point O as well, not just the forces themselves. So again, we could do R cross F. R would be simple for each one of these. It would just be, have a J hat component, and then we'd have to represent each of these as vectors and do R cross F. Or we can just do this with the 2D method, do it from a scalar standpoint. Let's do that. But it's the same idea. We're saying, what's the moment of this force about point O? Get that as a vector. What's the moment of this force about point O? What's the moment of this force about point O? Sum all the net moment of these three forces about point O, and then put that moment at point O. So you have this resultant force at point O, this resultant moment. You can put that resultant force and moment at point O and then remove these forces, and you have a statically equivalent system, or rigid body mechanics equivalent system. Okay, so we can break this down like this. This has just an X component, right? So this is just creating a moment about, well, okay, in a 2D system, when you're talking about moments, we discussed this. It's simplified in the sense that the moment axis, if for a planar system, there's only one moment axis. It's coming into or out of the plane, right? Because the forces are in the plane. It's a 2D system. The forces are in that plane. So the moment axis is coming into or out of the page, into or out of the plane. That's why it's like a scale. That's why they call it a scalar analysis, because we're only going to have the moments of these forces are going to be positive or negative, because the moment's going to be about the axis coming into or out of the page. So, okay, coming into or out of the page, this here is just this force times this distance. This force here, the Y component, has no moment about point O. Same here. So to get to sum the moments, we'll say, okay, the resultant moment about point O, and this is technically a vector. All moments are vectors, but sometimes they don't mention it as a vector in 2D because it's inherently implied that the axis is coming into or out of the page. You just put a positive or negative sign in front of the moment. But so, okay, right-hand rule, the positive moment is going to be counterclockwise, right? Curl your fingers in the direction, counterclockwise direction. The thumb is pointing out of the page. That's positive Z. So, okay, we've got summing the moments of all these forces about point O. We've got minus 200 times 2, right? This is a clockwise negative moment. This is going to be counterclockwise, so positive moment, plus the X component of this force is 4/5 times 150, and then times the moment arm, 4, and then this is going to be a negative moment. You've got 300 cosine 30, and then times 6. And then that's it. There's no other moments. There's no, the Y components here don't have any moment about point O. Okay. So minus 400 plus 4/5 times 150 times 4 minus 300 times cosine 30 times 6. And then this is so minus 1,479, that's pounds feet. We can put that in kip feet. So minus 1.48 kip feet. And again, I want to emphasize this is a vector. This is a vector. This is a vector pointing into or out of the page, but in this case, it's into the page in the negative z direction. And by the right-hand rule, we know that that means that it's clockwise. So the moment you got a resultant force like here, and then a moment clockwise here. And remember what this means. The idea is, this is not, as shown here, this is not an equivalent system as it was originally when we started this problem. Now it's an equivalent system. It's statically equivalent. And actually, to be more specific, I would have to put theta. So this FR at that theta, and then this moment, I mean, maybe I would take the negative off, and because if you leave this as negative, you might be saying, based on this diagram, that, okay, it's negative, so it's in the opposite direction of what's shown here, but you get the idea. That's equivalent to the initial system. If you remove those forces and put this, statically equivalent from a rigid body dynamics standpoint. And again, don't get bogged down thinking, oh, well, we couldn't actually apply these forces in real life. You know, come here with some twisting machine and a winch and put these forces and it would be the exact same. Yeah, because the deformations right in the regions where the load is applied would be different. And, you know, it's not like that, though. We're thinking about this as a rigid body, and we're just doing a static analysis. Yeah, if you applied the forces here, you would have all these local deformations would be much different than if you had forces applied here, and the local deformations would be here. But we're not looking at local deformations. We're in statics, dynamics, rigid body mechanics.